You know, our whole modern world pretty much runs on light, zipping through these impossibly thin strands of glass called optical fibers. They carry everything, your internet, critical medical data, you name it. But what happens when you need to send that data through places where normal technology just, well, where it melts or freezes or just falls apart? And that really is the big question, isn't it? How do you keep a perfect, clean signal when the world around your cable is doing its absolute best to destroy it? This is a massive challenge for aerospace, for advanced medical devices, and for all sorts of cutting-edge science. So let's talk about these breaking points. We're not talking about your cozy, air-conditioned server room here. No, we're talking about the inside of a high-powered industrial laser, or a high vacuum chamber for a critical experiment, or even a probe that's exploring the solar system. These are places where standard tech, it just can't hang. So you take a conventional fiber optic cable, the kind that probably brings the internet to your house, and you throw it into one of these environments. It's like a gauntlet. At 400 degrees Celsius, its protective plastic coating literally melts. In a high vacuum, it starts releasing gases that can ruin an entire experiment. And if you try to sterilize it for medical use, it degrades and fails. It's just not built for this kind of abuse. Now, you'd think the weak link here is the delicate glass core itself, right? I mean, it's super thin glass. But nope, that's not it. The high-purity silica glass is actually incredibly tough. The real problem, the fatal flaw, is the plastic jacket that's wrapped around it, the very thing that's supposed to be protecting it. That standard polymer coating, it's the fiber's Achilles heel, for sure. It's just mechanically weak, it melts, and this thing called outgassing is a huge problem. In a vacuum, the polymer basically sweats out these tiny molecules that can fog up sensitive lenses or contaminate scientific instruments. The protector becomes the problem. So how do you fix it? Well, the solution is actually pretty brilliant in its simplicity. You don't have to reinvent the glass fiber itself, you just give it a totally new kind of protection, a new coat of armor. And here it is. Meet the aluminum-coated fiber. It's the exact same high-quality glass on the inside, but on the outside, it's wrapped in a thin, seamless layer of metal. It's like a flexible, perfectly sealed suit of armor for the light signal inside, shielding it from a really harsh outside world. So this new armor, it gives the fiber some incredible superpowers. And the first one, which is just astonishing, is its ability to handle insane temperatures. Okay, on the cold end, this fiber works perfectly at minus 270 degrees Celsius. I mean, that is just mind-numbingly cold. We're talking cryogenic temperatures, literally colder than the vacuum of deep space. And the signal? It just keeps on flowing, no problem. But here's the really wild part. The exact same fiber can operate continuously at 400 degrees Celsius. That's hot enough to melt lead. The sheer range here, from the absolute depths of cold to blistering heat, is just immense. So how does one simple change do all of this? Well, let's break it down. First, strength. It's metal versus plastic. It's just physically tougher, period. Second, stability. A solid metal coat can't outgas in a vacuum. Problem solved. Third, heat management. The aluminum is great at pulling heat away from the core. And finally, integration. You can actually solder this fiber directly into place, which gives you an ultra-secure connection with no messy epoxy. And the list just keeps going. It's compatible with every major way of sterilizing things, steam, radiation, all of it, which is a huge deal for medical devices. It can handle 100% humidity, and it has incredible resistance to the kind of constant vibration and stress that would just wear a normal cable out. It is absolutely built to last where failure is not an option. So that brings us to the big question. Where do you actually use a superfiber like this? This isn't for wiring up your office, right? This is for technology that's way out there on the cutting edge. And this is where it gets really cool. We are talking about aerospace systems, where reliability can be a matter of life and death. We're talking medical devices that have to be perfectly sterile and reliable. High-power industrial laser systems, super-sensitive scientific sensors sitting in vacuum chambers. These are the fields where this armored fiber makes new innovations possible. You know, this quote from the source material just says it all. This fiber was, quote, designed for use where conventional polymer-coated fibers fail. That's it, right there. This isn't just a slightly better cable, it's a specialist, specifically engineered for the breaking point, for the exact moment everything else gives up. So let's do a final showdown. When you put them side by side, the difference is just stark. Max temperature, how it works in a vacuum, mechanical strength, longevity. In every single category that matters for these extreme jobs, the aluminum-coated fiber isn't just a little better, it's in a completely different league. It is the definition of a high-performance solution. And all of this leaves you with a really fascinating thought. We've just seen how a simple metal coating can turn a standard component into something truly extraordinary. So as we keep pushing further into space, deeper into medical science, toward more powerful technologies, it really makes you wonder, what's the next everyday component that's going to need its own suit of armor to keep up with our ambitions?